Okay, so today we're looking at question 2 of the 2018 MAT paper. This is going to be a bit of a longer video because this is the first long question of the paper. And we have 5 separate parts to this question. So let's go ahead and read it. We have 2 transformations, s and t, and these are given below. So s of xy equals x plus 1y, t of xy equals minus yx. And we'll have a look at what they do in a second. And then they define what the composition of 2 transformations is. Just what you'd expect. You just write the 2 letters next to each other and you compose the 2 transformations. And we also have the power of a transformation. So t to the power of n is just t applied n times. So for the first part, part I, we are asked to show that ts of xy does not equal st. So essentially saying that these transformations don't commute for all xy. So that's the first part of the question. Right, I've written the 2 transformations up here. We have s and we have t. So let's have a look at what they do in the xy plane. So these rules are defined for general coordinates x and y. So if you look at s first, we take a coordinate pair. Let's say this is xy. And then the image of s is x plus 1y. So we're essentially shifting all the points to the right by 1. So this would be x plus 1y. So the transformation x is a horizontal shift to the right by 1. That's fairly simple. T is a little bit more complicated. Let's have a look at what it looks like. We've got the plane x, y. So let's take a random coordinate, say over here. This is x, y. And now this, the image of t is minus y, x. So there's 2 things going on here. We've swapped the coordinates x and y, and we've also got a minus sign in the first slot. So we can think about this as 2 transformations essentially. If we draw the line here, y equals x, then we've first reflected it in the line y equals x to get the point yx, and then we've applied the minus sign to the first coordinate, and that's essentially the same as reflecting on the line x equals 0. So this is the line x equals 0, this is one of the axes. And if we reflect it across this, we're going to change a sign in the first coordinate. So this will give us something like this, minus yx. And this is the image of t. So this is a bit more complicated. We've got 2 reflections going on, but we know what it does. So if you remember the first part of the question, we need to show that s and t don't commute. So to do that, we just calculate the composition of s and t, and then t and s. So sty, this is apply t first, and then apply s. So if we apply t, this is just given by the rule up here. We have s composed of minus yx. So here we've just applied the transformation t, and that's how we got this coordinate pair. And now we need to apply the transformation s to this coordinate pair. And s is just add 1 to the first component. So we have minus y plus 1x. So this is what st is in general for all x, y, all coordinates. And then to show it doesn't commute, we need to calculate ts as well. That's not very good written t, sorry. Ts applied to coordinates x, y. So we first apply s. So we have t composed with s is just x plus 1, y. And then we apply t to this new coordinate, x plus 1y. And what do? We switch the entries and then we apply a minus sign to the first component. So we get minus y, and we have an x plus 1. And we can see that these 2 aren't going to equal for all x, y, just because, for example, we've got a plus 1 in the x coordinate for the first transformation and then a plus 1 in the second slot. So we can show this explicitly for, you could say, for example, for the coordinate 0, 0, st of 0, 0 is going to be 1, 0, whereas ts of 0, 0, that's going to be 0, 1. And these don't equal. So that shows that t and s don't commute, and that's the first part of the question. Okay, so going back to the question, let's have a look at part 2. So this is asking, for what values of n is it the case that t to the power of n of xy equals xy for all xy? So remember that t to the power of n is the transformation t applied to itself n times. So we're essentially asking for what values of n is t to the n the identity map. So it's mapping all its points onto themselves. So it essentially does nothing. And this is what we're going to look at now. Okay, so we can start off by working out a few powers of t and seeing if we can find a pattern. So we have, let me just write out t again, t of xy is minus yx. Now let's compute t squared of xy. And this, just remember, is t applied to itself twice. So it's t applied to the image of t minus xy. And then we apply t again. So we need to be careful here. What does t do? It swaps the coordinates and it applies a minus sign to the first slot. So if we swap these two, we're going to have x minus y. I've just swapped the two coordinates. And then we apply a minus sign to the first slot. So we're going to get a minus x here. So this is what t squared is. And we can see that the x's and y's are in the right position now. They've just both got minuses. So we can also think about this as a reflection in the line y equals minus x. So if this is y equals minus x, then if we have a random point x, y, then the transformation of t squared is going to be minus x minus y down here. So we've just reflected in this line. That's another way to visualize this. But we need to find when does t to the power of n equals xy. So let's calculate a few more powers. T cubed of xy. This is, so it's t times t squared. So let's just write that, t squared of xy. We've just worked out what t squared is. So this is t of minus x minus y. And then we need to apply t one more time to this. So remember the rule. Swap the coordinates. We have minus y minus x. And then apply minus to the first slot. So we essentially remove this minus sign. So t cubed is y minus x. We're not quite there yet, so let's do another power. See what this leads to. T to the power of 4. So this, I won't write this step again, but it's t times t cubed. So it's going to be t times the image of this. So this is just exactly what we've done before. We split t to the power of 4 as something we've calculated already. So it's t times the image of t cubed, and this is the image of t cubed. So now we just need to apply t one more time to this coordinate. And again, remember the rule, swap the coordinates, apply the minus sign to the first coordinate. So we need to remove this minus sign. And we now are back to xy. And this is what we wanted to arrive at. So we've got t to the power of 4 of xy equals xy for all coordinate pairs. And if you can imagine, we can just iterate this process. So if we were going to have t to the power of n for any n, we could just split this into multiples of 4, and then that would just be mapping onto itself, and then we just have left over the rest of the multiple. So we can deduce from this that this is going to equal xy for all, that's right, for all multiples of 4. Multiples of 4. So to see that, we can just apply t to the 4 however many times we need, because n is a multiple of 4, so that means we can write n as 4k, for example, and then we just split t to the n as t to the 4 to the power of k. So what I mean by that is we could write t to the n as t to the 4 to the power of k. And then we see that since t to the 4 is just the identity map, it would just map xy onto itself again. So this is the answer, whenever n is a multiple of 4. Okay, so we've done parts 1 and 2. Now let's look at part 3. So this is asking us to find a transformation U that is composed of S and T, which is an inverse of S. So this is a shift to the left by 1. So we need to find certain combinations of transformations S and T in some order to get a inverse of S. So instead of going to the right by 1, we're going to the left by 1. And then after that, we've got another question, which is, what is the least number of applications of S and T in total that can produce U? So finding kind of a minimal combination of S and T to produce U. And then we need a little justification. So let's do this. Okay, so now we need to find a certain combination of S and T to produce U, which is a shift in the left direction. So let's just think about this carefully. If we have a graph here, so S would move this point to the right by 1, so this would be S, and then U would move it to the left by 1. So we need to kind of, intuitively, we need to use S at least once, and probably only exactly once, to move our original point by 1, but we also need to use it in conjunction with t to get a certain combinations of reflections, so that instead of moving to the right, we're moving to the left. So let's quickly remind ourselves from the last question what the powers of t looked like. So remember that t squared of xy was minus x minus y. And as we said, this was a reflection in the line y equals minus x. So intuitively, this might hint that we can apply this, and then we get a point. So if this is our original point s across x, and then we get a new point here, we've reflected in the line y equals minus x, and now the coordinates are negative. So if we apply s now, then we'd be moving it to the right here, but then if we apply t squared again, we'd be reflecting it, and that would kind of undo the action, and it would map it back to minus 1. So this would provide an inverse of s. So let's do a few calculations to actually see what I was meaning here. So if we apply s to this, then let's see what we have. S t squared xy. We just add 1 to the first components. We have minus x plus 1 minus y. And what I was trying to hint at before is if we apply t squared again, then we are going to apply negative signs to both coordinates. And this is going to make this plus 1 here minus 1. So let's do exactly that. T squared s t squared of xy, well, that's just t squared applied to what we had above, the line above, minus x plus 1 minus y. And then we know what t squared is. This is just put minus signs in both components, and the minus x is going to go to x, plus 1 gets minus 1, minus y goes to y. And this gives us exactly what we want. So just to conclude, u equals transformation t squared st squared. So I was trying to provide a little bit of motivation how to arrive at this answer. I hope that made sense. Essentially, we know we want to use s one time because we want to move the point to the side by 1, and t squared only reflects. And then we need to use some combinations of t so we get the right reflections. And then we've moved the particle, the coordinate, to a reflection in the line y equals minus x. Then we move to the right, and then we reflect it again. So this kind of makes this move to the right to the left, essentially. That's all it's doing. And remember that the last part of the question was to justify that this was the optimal combination. So we can't do this. So we've used t and s 5 times here, and the last part was to justify why we can't use any less times. So as I was hinting at earlier, we need to use s one time, so s once, to displace the coordinate by 1, but we also need we can't use any combinations of t less than 4, so we need t 4 times, and the reason for this, it's a bit subtle. Essentially, t is a reflection, and we saw earlier that t to the power of 4 is the identity. It kind of maps the points onto itself. So we need to use 4 applications of t to get the right orientation of the plane. So remember, t was kind of a weird reflection, and to get back to the right orientation, we need to apply t 4 times. So whatever our combination, we need at least 4 values of t in here. And this is the right combination. So this kind of justifies why this is the minimal combination to generate u. We are now on to part 4 of the question, and this is to show that for any integers a and b, there is some sequence of applications of s and t that maps the origin, 0, 0, to the coordinates a, b. So we need to kind of show that there's a way to reach this pair of coordinates starting at the origin. So there's some combination of s and t to get there. Okay, let's think about what this question is really asking us. If we draw the plane, the xy plane, we're told that if we start at the origin, the point 0, 0, and we have an arbitrary coordinate, let's call this a, b, that there is some path to get here from 0 to ab using applications of s and t. Now remember from the previous part, we've constructed u, which is a way to go left by 1, and we also have s, which is a way to go right by 1. So now we have ways to move along the x-axis by plus or minus 1, and intuitively this means we can get to any x value that we're given. So for any a, we can move along this axis and we can arrive at a. But we don't have a way to move vertically. So if we could find the way to move vertically, if we could find a way of using s and t to go up by plus 1 or go down by minus 1, then we could reach any integer coordinates a and b. So this is the way I'm going to approach this problem. We're going to try and find a transformation that goes up by 1. So instead of x minus 1y, we have x y plus 1. To do this, remember what u was. We found this in the previous question, and we found that u was t squared s t squared. And we said that we needed t in here 4 times, so we had the right orientation, and we needed s to move the particle by 1. So we're going to try and use a similar strategy to go up and down by 1. We need to use s at least once to move the coordinate by 1, and we need some combination of t to move upwards instead of side to side. But we're going to need t applied 4 times so we have the orientation correct again. So let's just try different powers of t. So if we try, for example, t cubed st, then this satisfies our conditions where we use s once and t 4 times. And let's see what this maps it to. So let's just do this. So t cubed s of, we know what t is, that's minus yx. And we know what s is, t cubed, okay. We just add 1 in the first coordinate. And if you remember what t cubed was from earlier, let me just write this over here. So t cubed of x, y, this was transformation y minus x. So let's apply this rule to this coordinate pair. We essentially swap the 2 values, and then we put a minus sign in the second slot. So x, and then we're going to need minus times this stuff. So we're going to have y minus 1. Okay, so that's really good. So we found a way to go down by 1. This transformation maps x, y to x, y minus 1. So this gives us exactly this transformation down by minus 1. So the last thing to do is we need a way to go up as well in case b is positive. So let's try the last combination we haven't tried, which is t s t cubed. And then if we apply this to x, y, let's just do the calculations. t s t cubed over here is given by y minus x. And then apply s to this, y plus 1 minus x. And finally t applied to this, swap and put a minus sign in the first slot. The double minus cancels, and we're going to have x, y plus 1, which is brilliant because this gives us a way of going up by 1. So now we have, if you think of having like, when you play a game and when you have controller, we have a way to go up, to the right, left, and down, then that means we can essentially move anywhere on the plane. And this is exactly the idea behind this question. Starting at 0, we can apply these transformations however many times we need to reach a and b, but we can do this for a finite sequence of combinations, which is what we want. Okay, so now we're on to the final part of question 2, part 5. And we are told that we have a parabola C with equation y equals x squared plus 2x plus 2. So this is just a very simple quadratic. And we're asked to work out firstly, what is the equation of the curve obtained by applying the transformation s to C. So what does this parabola look like if we've transformed it by s? And secondly, it's the exact same question, but if we use t instead of s. So let's look at this. Okay, so I've written the equation of our parabola f of x equals x squared plus 2x plus 2. So let's just quickly remind ourselves what this means, and this is going to be important for the rest of the question. This means if we take a value of x, some random value of x, let's say this is x, and this function gives us the height of this parabola, and this, for all values of x, this would map the parabola onto the xy plane. So let me just write this as y. So this is kind of what we mean by a function. This is going to be important when we look at applying s to this. So with this idea in mind, we can write any point on this parabola as x f of x. So we take the x input, and f of x gives us the height. It gives us the y coordinate. This is just what we've drawn here. So now we've written it like this, we can actually work out analytically what the image of S under the transformation S is. And we do this, we just add 1 to the first component, we get x plus 1 equals f of x. So if we could try and rearrange this, think of it slightly differently so that we've got a single variable here, then in the second slot, it'd give us the function that is the transformation. So by that I mean if we let t equals x plus 1, so let me just write this here, let t equals x plus 1, we've got a single variable in the first component, and then we need to think about what the resulting substitution is in the second slot. This is going to be f of t minus 1, just because x equals t minus 1, just rearranging this. So thinking about what we had earlier, we now have t in the first slot and we have f of t minus 1, which this kind of maps to a new function. So, and we know what this transformation does. This moves it to the right, which is what s did anyway, so that agrees with our intuition. So this would map the whole parabola to the right by 1. I'm not drawing this to scale, but this is kind of what this transformation does. And this gives us exactly this coordinate here, tells us what the new equation of the transformation is. So if we just work out what f of t minus 1 is, just by substituting into this equation, we have t minus 1 squared plus 2t minus 1 plus 2. And then we can expand this out and simplify. We have t squared minus 2t plus 1 plus 2t, we're going to get some cancellations, minus 2 plus 2. And so we get, in the end, the transformation is t squared, we have no values of t, and then we have plus 1. So just to summarize what we've done, we've written this parabola in its parameterized form in the coordinates x, f of x. We've applied s and worked out what it is analytically. And then we've used a substitution just to express this new point in terms of something we can express as a function. So this, we know that under this this notation, that the transformation, the y coordinate, the height, however you want to represent it, is given by this function, so f of t minus 1. So if you take a coordinate, an x value, well, we've written it as t now, but then the height is going to be t squared plus 1. So this is kind of what the new parabola is. So this is the effect of the transformation of s. So we have the original parabola c, and we have this new parabola c dash, for example. And this is the equation of the height of that. So I'll just stress that there are other ways of getting to the answer. We can, you could just skip this whole step and just realize that s is a transformation to the right. So this is intuitively what we're going to get. We're going to replace x by x minus 1 or t minus 1. So that's another way to think about it. I've just done it analytically so you can see all the steps. Let's look at the second part now. Okay, the second part is a little more tricky. We want to find the image of our parabola under t, but we're going to apply a similar approach. So if we write our point on this parabola as x, f of x, then apply t to it. Let's see what it does. We have, just using this rule, we have minus f of x and x. So this is a bit tricky because now we can't really use a nice substitution just to get it in terms of one variable in the first coordinate. What I am going to do is I'm going to write this in terms of new coordinates. I'm just going to write this as uv. And let's just write out what u and v are. So u equals this function minus this function. Actually, let me just factorize this a little, just to simplify a little bit. We have x plus 1 squared plus 1. That's just a bit simpler form. So we have minus this. We have minus x plus 1 squared minus 1. This is what u is, just by equating the coefficients. And then v is x. So luckily, the second component is actually really nice because it's just x, which means we can try and express u in terms of v, which is very easy. We just replace x by v. So this tells us that u equals minus v plus 1 squared minus 1. And now this gives us a rule that tells us what the image of our parabola is. So this is a bit complicated. Let me write this equivalently so it might look a bit nicer. We've written uv, but we can think about this as xy, sorry. I've just used different letters so we're not confusing with our original x's, but this is equivalent to x equals minus y plus 1 squared minus 1. So this is a bit strange because normally we'd have a function in terms of x, but now think about this slightly differently. We are given a point on the y-axis, so our input variable is a height. So somewhere along this axis we're given a value of y, and this tells us how far along the x-axis is. And this is fine because this kind of defines our parabola. So as before, we could equivalently think about this, just what the transformation t does. So you could plot the function f, and then remember that t was just a reflection in the line y equals x. So we'd get firstly a parabola that looks like this, and then it was a reflection in the line x equals 0. So this is a bit messy now, but the resulting parabola would look very roughly something like that. And this is what maps, this is the equation that maps this parabola here. I'll call this g, for example. And it kind of reflects that we can't write this as a nice function in terms of x because the parabola is lopsided, it's on its side. So for one value of x, we have two heights where this equation is satisfied. We have two values of y. So that's why we have to kind of flip this problem on its head. We think about y as the input, and then for one value of y, we have exactly one horizontal coordinate satisfying that, the x value.